So in this video we're going to talk about chapter number 1, which is matter, energy and measurement, and we're going to talk about what matter is, how what matter is made up of, and what is energy, and then how we normally do a measurement, right, and why this is important. So let's start with the matter. So how we define matter? So matter is anything that has mass and take up some space or volume. For example, look around you. The chair that you are sitting on is also a matter. Why? Because chair has some mass and is occupying some volume, right? The pen, if you are holding a pen, pen is also a matter. Why? Because pen also has some mass and occupying some space. The chair, the bench, right, and the TV, whatever is like surrounding you, everything is made up of matter, right? So now we're going to talk about if we have a, let's say, a matter, and if we keep on slashing down the matter, if we want to go inside the matter and see what matter is made up of, we're going to end up with one special unit called atom. So atom is the ultimate unit of matter. That means matter is made up of atoms, and we're going to talk about atoms later on in the course, right? Then we have a substance. Substance is nothing, is a special type of matter. For example, air. Air is also a matter, right? Blood is also a matter. So these are the specific type of matter, what they are made up of, right? Then we have the states. So matter can be found in 3 states that we can say as, if we talk about matter can be found in 3 states: solid, liquid and gas. And we're going to talk about these things in the next slide. And then if we talk about the scale, then we can study the matter at atomic level as well as the macroscopic level. What is atomic level? That we cannot see by our naked eye, cannot be seen by naked eye, right? These are the atomic level made up of atoms. Macroscopic study normally, or is macroscopic matter, is that we can see by naked eye, right? This include maybe a human body. You can see a human body, right? So this is a macroscopic scale of the matter, right? And then if we have some diseases, for example, in our human body, that may be because of the some malfunction at the atomic level. There's some deficiency at the atomic level, right? So let's go to the next slide. Then we're gonna talk about what are the 3 states of matter that we just discussed on the first slide. Like I already told you, matter can be found in 3 states: solid, liquid and gases. So these are solid, liquid and gases, right? The top one is in the macroscopic view, means the outer the physical appearance of the matter. And the second one is at atomic scale, how the matter is made up of, right? How the arrangement of atoms within the atom, because as we know that matter is made up of atoms. So in solid state, particle of the matter, basically particles can be as an atoms are close together and are in order arrangement. If you see the solid over here, if you can see that all the particle, or you can say the atoms, are perfectly aligned or in a order arrangement, right? They're very close together as a tightly packed. Whereas in liquid state, particles are in a disorder arrangement but interacting with other particle. For example, if you can see in the liquid over here, the atoms or the particle are still close to each other but not as close as that they normally found in the solid, right? So they can move around like around each other, but they are still interacting somehow, right? That's why the water or the liquid can flow. And the third state of matter is the gas state. And in this, particles or the atoms are far apart and interacting only during the collision. Right? If you can see the last structure over here, the atomic scale, the atoms in the gas are like very far apart compared to the solid over here. So there is no kind of interaction between the atom or a particle of the gas molecule, and they are just moving around separately, right? They usually don't interact with each other until or unless there is some kind of collision between them, right? That's why the gas can flow, because there is no interaction between them, right? Can you give me one? And so if we talk about the example of the solid, can I say the skin and body? Skin and the bone of a human skeleton, they are like a solid because the atoms are tightly packed. If we talk about the liquid, can I say the blood in our body is a type of liquid because they can flow, right? And the last one that we can use an example for a gas is like an air that we breathe in, because the particle or the atoms in the air are very far apart, right, not interacting with each other. So this is how we normally study the matter at macroscopic scale as well as the atomic scale. Right. Now let's talk about the energy associated with the matter. What do you guys think? If we have a matter, let's say a pen, what do you think, the atoms or the particle within the solid object like a pen is in stationary form? No, because the particle of the matter are not stationary. In the solid, they may be vibrating. For example, this is a solid. You have the particles or atoms that are very close to each other. Right? This is a solid. So these particles can be vibrating up and down, left and right, right? But they cannot leave their space, right? Similarly, in liquid, the atoms can be moving around, right, with some kind of energy. And in gases, particle, as we already know, the gas particle are moving around randomly. And why all these particles are vibrating and moving out? Because of some kind of energy associated with these particles, right? So that's why energy and the matter, if I say energy and matter, they're connected by a relationship, right? Because if matter has energy, the atoms or the molecule or the particle are vibrating or moving around, right? So there are two kind of if we talk about now the energy definition, what is energy? Like we already seen the relationship between energy and matter. Now let's talk about the energy. What is energy? Energy is the capacity to do a work. If you want to do some kind of work, you need to use some kind of energy, right? And what is work? Work is an act of moving an object against an opposing force. For example, if you see this picture over here, the nurse is trying to pull the wheelchair of the patient against the friction of the road, right? So the nurse is doing some kind of work, right, by moving the wheelchair, right? So we can divide energy, or energy can have a two basic form. If we talk about like this, energy has two form. One is called kinetic energy, second we call as potential energy. Potential energy, right? So now we're going to talk about what is kinetic energy and what is potential energy. So let's talk about the kinetic energy first. So kinetic energy is the energy of the motion. Whenever you move, run, you have some kind of kinetic energy. For example, at the macro scale, for example, a moving car, whenever you drive a car has a kinetic energy, right? But if we talk about at atomic scale, we know that matter is made up of atom or particle. If the particle or atom are moving around vibrating, that means those particles also have some kind of kinetic energy, because atoms and particles are also moving, right, across. Right. So if we talk about all the three states of matter, whatever we studied in the previous slide, we know matter can be of solid, liquid, and gas. So the particle in the gas phase has higher kinetic energy compared to the liquid, and liquid is higher compared to the solid. So if we compare the kinetic energy of the particle in gas, liquid, and solid, this is the sequence: gas, solid, and liquid and solid. Right. So now let's talk about the temperature. How you define temperature? Temperature is nothing, it's just a measurement of average kinetic energy of the particle of the matter. So if any matter has a higher or like high kinetic energy of the particle, that means that matter has higher temperature compared to compared to that matter that has lower kinetic energy, right? For example, let's take, you have two matter, this is one, this is second. If the particle in the first has more kinetic energy, means they are moving faster compared to the particle or atom on the second, they are moving slower movement. So that means the matter 2 has lower temperature compared to the matter 1 that has the higher temperature, because the average kinetic energy of the particle in matter 1 is higher, right, compared to 2. So this is how you normally define a temperature. Now let's talk about the heat. If we talk about the heat, what is heat? Heat is the kinetic energy transfer from a matter at high temperature to a matter of low temperature. What does it mean? It's just the movement of the heat is the movement of the kinetic energy from one matter to another matter. For example, again, let's say you have two matter 1, and then you have connected a second matter 2, right? So this matter has high kinetic energy. If matter 2 has lower kinetic energy, Ke, so the energy is going to move from 1 to 2. This is the energy, right? Because for matter 1, if matter 1 has a higher kinetic energy, that means it has higher temperature compared to the matter 2 that has lower kinetic energy. So the heat is always goes, this is higher temperature, high temperature, matter 2 has lower temperature. So that means the energy or heat is going to move from matter 1 to matter 2. That means from higher temperature to a lower temperature, right? That's why it says heat always from hot to cold, right? Hot is higher temperature to a lower temperature. Now let's talk about the second form of energy, which is a potential energy. Potential energy is a form of stored energy. And it's because of its position or composition. For example, let's take an example in this picture. Let's assume we have a ball placed on the top of a hill, and because of the position of this ball from the surface of the earth, it has higher potential energy because of the position of this ball from the surface of the earth, right? But this because of this high potential energy, this ball is unstable. So if you just push the ball is gonna go down, and the potential energy is going to convert into a kinetic energy. Why? After you push the ball is going to roll down across the hill and then going to reach at the bottom of the hill, right, which has a lower potential energy, because now the position of the ball is same as the position of the earth's surface, right? So that's why what we learn from this picture is, at the top of the hill, ball has a higher potential energy because of the position of the ball. At the bottom of the hill, ball has a lower potential energy, right, because of position. But what we can see over here, then the potential energy is converting into a kinetic energy, right, during the process of the ball to reach from top to high. So we can say that the two form of energy can be interrelated, or you can change from one form to a second form. That means kinetic energy can be converting into a potential energy, and potential energy can be converting into a kinetic energy. They are interchangeable, right? So remember this thing, this is very important. You cannot create the energy, but you can convert one form of energy into a second form of energy, right? Okay. Now let's take some of the example and figure it out which kind of energy is associated with them. A compressed spring. If you compress the spring, that means you are doing some kind of work, right? You are compressing the spring, and because the spring is compressed, you have some kind of energy stored in the spring, and that kind of energy we call as a potential energy, right, because of the position of the spring. The second one is a windmill turning. If the windmill is turning, that means is the energy of the motion. We call that one is a kinetic energy. The C part is particle in the gas state colliding with the walls of the container. If the particle of the gas is keep on colliding with is moving fast, colliding to the surface of the container or wall of the container, that means this is a form of kinetic energy, right? They are colliding because of the movement. A skier skiing down a mountain, kinetic energy again. And a pasta prepared for a meal. So if you have a meal, that means you have some kind of energy within that meal, right? So the energy is stored in the form of potential energy, and because whenever you eat, you get some energy because of the meal, because that meal has some kind of energy already stored within it. So this is a kind of potential energy. So if you see, these are the answer that we already discussed in the previous slide: potential, kinetic, and potential. So now let's talk about another term called scientific notation. So before we go into what is scientific notation is, so let's take an example. If the number is, we normally work with a smaller number, right? Let's say 2345, or we can get a little bit bigger number, something like that, 100,000, right? But sometimes the number is so big, is very, let's say if the number has many zeros, right, you cannot write the same number and again in any kind of mathematical operation, right? Multiplication, division, or if you want to use it, this many number of zeros or this number multiple time, there is a high chance that you might be missing couple of the zeros, and if you're missing couple of the zeros, then your calculation might be wrong, right? Similarly, if you're working with a number that is very small compared to the regular number, for example, if you have any number 0.0000000005, you also cannot use this number in your calculation regularly, because there is a high chance you still miss some of the zeros, right? So to work with these kind of number that is very large or very small, and then to convert those number into that number that we can easily manage, we normally use a scientific notation. So scientific notation help us to convert a bigger or the smaller number into a workable number, right? So now let's see what is scientific notation and how we can write. So scientific notation has two part. one is called coefficient, which is y, and the second one is exponent part, right? So what is coefficient part? A coefficient is so the coefficient should be a number between 1 and 10, and then exponent can be positive, can be negative, but it has to be a whole number like 1, 2, 3, 4, 5. Right? For example, let me give you one example. 1.5 10 to the power 4. This is a type of scientific notation. This we call as coefficient, or sometimes we normally call as coefficient as a decimal number too. And this part 10 to the power 4 we call as exponent, right? So right, so this is how you normally write any scientific notation. And then and if I give you another example, something like 4.5 10 to the power negative 7, this is also a type of scientific notation, because this number over here is a coefficient and this number is an exponent, right? So let's try to do some example on this, and then we'll go forward from there. Okay, so we're gonna learn how to convert any number into a scientific notation. So let me give you one number, 1 2 3 4. This is a regular number, right, without any exponent. But if I want you to convert this number into a scientific notation, so what you need to do first, if you always look where you have any decimal point in the number, but in this case you don't have any decimal point, so you always assume the decimal at the last number. So if we assume there is a decimal number at the last number of the last digit of the number, and we have to move the decimal somehow between the first two non-zero number, which is 1 and 2. So if I move 1 2 3, so I can say that number as 1.234. and then how many times you move the decimal? I moved one time, 2 time, 3 time. So then you have to write 3 on the top on the exponent, right? So this 3 normally tells you how many times decimal moved, right? Now the second thing is that whether this 3 can be a positive 3 or a negative 3. How would I know this is a positive 3 or negative 3? So remember this thing, if you move a decimal from left to right, the exponent will be a positive number, plus 3. So if it's a positive number, we usually don't show a positive number, right? We just write 3 or 2 or 1 or 5, whatever the number you're getting, but we usually don't show a positive, right? Let's take one more example. If I have this number 45000, something like this, how would you convert this number into a scientific notation? So before we do this example, let's back to the previous example. If you can see over here, this number is between 1 and 10, right? This number is bigger than 1 but lesser than 10, right? So this is how you normally do scientific notation. So now let's back to the original problem over here, which is 45,000. How you're going to convert this into a scientific notation? So we don't have any decimal. We assume a decimal at the last digit of a number, and let's see how many times we have to move this number to move or place this number between 4 and 5. 1 2 3 4. So the number will be 4.5000 times how many times you move that decimal? 1 2 3 4. So you have to write 4 on the top of the 10, right? Like I said, this is how many times you move the decimal. Now the question is, this 4 is negative or positive? It's again positive because we move the number from decimal from left to right, right? So this is your scientific notation. If you see one more time, this number is between 1 and 10, which is 4.5, right? So this is how you normally do it. Let's do this other way around. If I give you any other number, 0.00153, this is also a number, and I want you to write into a scientific notation. So how would you do that? So this time the decimal is over here. Now we have to move the decimal between the first two non-zero number, which is 1 and 5. So let's move it 1, 2, 3. So the number will be 1.53 times. How many times you move the number? You move the number 3 times. Or move the decimal 3 times. But now you have to decide whether this 3 is still a positive 3 or negative 3. So it's gonna be a negative 3. So remember this thing. If you move a decimal, yeah, this is my bad. On the top, this is from right to left. This is from right to left. So yeah, so remember this thing. Correct this way. For the first example, you're moving the decimal from right to left, not left to right. Right? So now let's get back to our current problem over here. So right now we are moving the decimal from left to right. Right? So whenever you move a decimal from left side to a right side, the moment is like this, then your number will be a negative number on the top of the x, which is this one, negative 3, because you move the number 3 times. Right? So this is your scientific notation. If you see this thing, this is the number between 1 and 10, right? Because this is 1.5, more than 1, less than 10. Let's do one more example on this. 0.157. How are you going to convert this number into a scientific notation? Again, follow the same step. This is your decimal. Move this decimal 1 time, because after just one moment you're gonna get the decimal between 1 and 5, two non-zero number. So this is gonna be 1.57. How many times you move the number? 1 time, and you're moving from left to right, so that's why it's a negative 1. Right. So let's do one last example on this. If I have any number 0.00000075, what should be the scientific notation? Let's see how many times I have to move the decimal. 1, 2, 3, 4, 5, 6, 7. So it's 7.5 times 10 to the power 7, and we are moving a decimal from left to right, left to right. So it's gonna be a negative number. So this is your scientific notation, 7.5 10 to the power negative 7. So just practice this type of problem to convert a regular number into a scientific notation. Okay, so now let's go to another topic called unit and measurement. So whenever we study a matter, we need to measure it, right? Whenever we want to study let's say a pen, we need to know what's the length of this pen is, right? What the mass of this pen, how many grams, how many pounds this pen is. So that's why whenever we need to study a matter, we need to measure it. So there are two kinds of measurement that the scientists or the medical professional normally use. One of them is a English system, second one is a metric system. So English system is we normally use in the US, in the United States, but metric system is the main system that normally used in medicine and science across the world. Across the world. And then we have the SI system, which is also called as international system based on the metric system, right? And this is normally used by the scientists. Right. Then the next thing is whenever do a measurement, whenever you measure something, you will have two parts. One is called a number and the second part is a unit. For example, if you want to measure, let's say a pen, using a ruler, you normally write something like this, 2.5 centimeter. So this 2.5 is your number and then centimeter is your unit, right? So what is unit? Unit normally indicate the type of quantity measured and the system to measure it, right? So if we, so we'll talk about the unit a little bit later, but just right now, just know this thing. This unit normally tells you which quantity is being measured and what out of the two system, English or metric system, which system is being used to measure that quantity, right? So now let's talk about the metric system. So the metric system contain a set of base unit, right? And it donated by a one letter symbol, right? So what are the quantity we use in the metric unit? The first one is length, second is mass, third is volume, fourth is time. So if we talk about the length, the basic unit that we used to measure a length in the metric system is a meter. And the symbol of meter is a small single letter m. If we want to measure a mass, which is a quantity, then we're gonna use a gram as a unit, right? A symbol is G. For volume is liter, symbol is L. For time, second, symbol is S, right? And we call those M, G, L, S as a base unit. So we just talk about the metric system, but there is some also like we studied in the previous slide, we have English system too, right? And English system we have, we may be using for length, we may be using miles, feet, inches, right? For mass we might be using pound. For volume we might be using a gallon, right? For time, still second, right? So if you see miles, feet, inches, pound, gallon, that means we are talking about our English system. But in metric unit it always meter, gallon, meter, gram, liter and second, right? So that you know the difference, what unit we are using or which system we are using. So let's see about one of the table. The first column we say is quantity, and the second one is English unit, and the third one is metric English relationship. Let's see about a couple of them. If we talk about the length, like I told you, in the English system it may be a feet or inch, right? Again for length, yard, feet, right? So you have different kind of unit in English system. And then if you can see, it says on the first one, it says 1 feet equal to 12 inch. So that means if we talk about a 1 feet or if we say a 12 inch, both are same, right? Same number or same measurement, but in different unit. One is in feet, one in inch. But if you say 1 feet or 12 inch, no difference. They are measuring the same length, right? And this equal sign, like 1 feet equal to 12 inch, this equal or this relationship we call as equivalency. Equivalency. Right? That means this equivalency normally tells that in one of the unit, the measurement in one unit is how much in the second unit, right? 1 feet equal to 12 inch. Similarly, if we talk about 1 yard equal to 3 feet, in yard, if we measure 1 yard, 1 is equal to the 3 feet, right? If we talk about the relationship between metric and English relationship, if we see over 2.5 centimeter equal to 1 inch, 1 meter 39.4 inch. That means meter is a metric unit, inch is a English unit, right? This is metric. So we can also compare the number between different system, right? Metric and English system, right? Now if you can see this table normally tells you about the matrix prefixes and multiplier. So now what is prefixes? Prefixes are a unique one letter code. If you can see over here, this is a one letter code that when preceding a base unit act as a multiplier to increase the number value by the factor of 10 or decrease the numerical value by a factor of 10, right? 10. So what does it mean? Then let's say, for example, if I have 1 meter, what is this m? M is a metric system base unit, right? Because the unit that we are measuring is in meter. But if I write 1 cm instead of 1 meter, what does it mean? This 1 cm is less than meter or more than a meter? So if you see over here, this c, the prefix, because we know this m is a base unit meter, but what is this c? C, if you can see over here, c is your centi, right? So what is centi? Is 10 is power negative 2, if you can see over here, right? Or you can say is 0.001, both has same meaning, right? So that means I can say a 1 centimeter is equal to 0.01 meter, right? Because I just converted this prefixes into a number, right? Instead of writing c, I'm writing 0.01, which is its value, 0.01, right? So that's so that means 1 centimeter is less than a meter, right? So this is how we normally use the prefixes. Let's take one more example. If I write 1 kilometer, so I know this m is a base unit, is a meter, but what is this k? This is a prefix that we put in front of the base unit to increase or decrease the base unit, right? But let's see what is k. K is 1,000. So I can say 1,000 and write m. So I'm just writing the number of k over here instead of writing k. So 1 kilometer is 1,000 meter. So that means 1 kilometer is more than a meter, right? Because by writing k, we are increasing the number by 1,000 times, right? So make sure you understand this thing: deci, centi, milli, micro, nano, pico, and then their number 10 is power negative 12, 9. So basically this table tells you the quantity that's smaller than the base unit, because everything is in negative. 10 is power negative 1, negative 2, right? Then we have another table. Then another table that if we put that prefixes, that makes the quantity larger than the base unit, right? For example, kilo, tera, giga, mega, right? For example, over here, if I say 1 megahertz, so instead of, we know hertz is a unit of frequency, but the time I write m, what is m? m is a mega, right, over here. So what is mega? Mega is 10 to the power 6. So instead of writing m, I'm writing 10 to the power 6 hertz, right? So increasing the number by 10 to the power 6. Similarly, 1 kilometer, the same example that I gave you in the previous slide, this k is your prefix, and instead of writing k, I'm writing the number 10 to the power 3, and m is still a base unit, right? So that means you are increasing the base unit of a meter by 1,000 times, because 10 to the power 3 is nothing, is 3 zeros, 1,000 meter, right? So that's why we normally use a prefixes. Okay. Now let's talk about some, again, for like couple of slides for the measurement. If we talk about the measuring of the length, the base unit we already know is a meter. We already did this example. 1 kilometer is 1,000 meter. 1 millimeter, if I write 1 mm, what is m? M is your prefix, and the prefix is milli, right? M. And what is milli? Milli is 0.001 or 10 is power negative 3. So you can write 1 millimeter as 0.001 meter, because instead of writing m, you are writing that number 0.001. Or you can write the same thing, 1 mm is equal to 10 is power negative 3 m. Right. Similarly, 1 centimeter, if I say 1 cm, what is c? C is a centi. Centi is 0.01 or 10 to the power negative 2. So you can write 1 centimeter as 0.001, or you can write the same number as 10 to the power negative 2 m, because you are just writing the number instead of the c, right? And they are equal, right? So whenever you see this kind of equivalency, like 1 kilometer is 1,000 meter, 1 millimeter is 0.001 meter, 1 centimeter is 0.001 meter. So all these equal number we call as equivalency, like I already told you, equivalency. That means they are equal, right? Now let's talk about the mass. Mass is a measure of the amount of the matter in an object, how much amount of that particular matter has, right? And the base unit of mass is a gram. If I say 1 kilogram is the same thing, k is 1,000, so 1 kilogram is 1,000 gram, g is the base unit. 1 milligram, so instead of writing m, we are writing that number, right? So I can say 1 milligram is equal to 0.001 gram, or I can say milli is what? 10 to the power negative 3, and just write g, same thing, right? So 1 milligram is 10 to the power negative 3 gram, and these number is also a equivalent number. They are equivalent number. Same for volume. The base unit for volume is liter. 1 kiloliter, 1,000. Same thing, k is your 1,000. Milliliter, m is 0.001, l is the base unit, right? So if we want to calculate the volume of any object, we can use a formula to calculate the volume. For example, if we want to take the volume of a cube, if we say over here, this is a cube, so the volume of the cube is always length times width times height, right? And if we are measuring the unit or the length, width and height is in centimeter, then it's going to be centimeter cube or cubic centimeter, because we have 3 centimeter getting multiplied, cubic centimeter. And one of the important equation that you need to use to solve couple of the problem is 1 ml is always equal to 1 cubic centimeter, right? So if I say 1 ml is same as if I'm saying 1 cubic centimeter, they are same, they're equal. And if they are equal, we can say this is also equivalent, right? Okay, so till now we just learned about that if we have any object, we can use a formula to calculate the volume of that object, right? But let's say if that particular solid or an object are irregular shape, if they're irregular, so that means if the shape is irregular, you cannot use the formula to calculate the volume of that particular object. So how would you calculate the volume? So we're going to use a special method called volume displacement method to calculate the volume of that particular solid, right? For example, let's take, if we have a cylinder with a volume with a liquid fill in it, and if we measure the volume within that graduated cylinder, let's say the volume right now is 5 ml, right? And if we want to calculate the volume of this irregular object, let's say this is irregular object, so how are you going to figure it out? You have to just drop that irregular object in that volume, and the time you drop that object, what's going to happen? Because of presence of this irregular object into the liquid, the volume of the liquid will rise, right? Now the final volume of this liquid, let's say for example, is 7 centimeter, 7 ml. So how would you know what's the volume of that object? So according to the volume displacement method, the volume of the object, irregular object that you dropped into a liquid, then the change in the volume of the liquid after you drop a solid object, that change in the volume of the liquid is equal to the volume of that object. That means how much volume change when you drop that solid object over here? It changed, final is 7, initial is 5, which is 2 ml. So the change in volume of the liquid after you drop the object is 2 ml. So that means according to this volume displacement rule, this is the volume of the object, volume of irregular object. Right. So the volume of the object can be measured by determining the volume of water that is displaced. So volume of object is what's your final volume after you drop the object, and what was the initial volume before you drop the object. You have to just subtract both the volume to get the rise in volume, right? That is the same as volume of the object. Okay, now let's try to do some of the problem that is given in the slide. Write the conversion between the first microgram and gram. So if I say what is micro, the time I see the micro written over here, micro has a symbol U, right? So I can say 1 microgram, G is gram, is equal to how many grams? So the time I see is a micro is what? 10 is power negative 6, and this is a base unit, it will be remain the same, G. So 1 microgram is 10 power minus 6 gram. If we can go again micrometer, so I can say micrometer is equal to 10 is power negative 6 meter, right? Because meter is a base unit. Then again we have a microsecond, micro S is your second, then it's gonna be again 10 is power negative 6 second, because micro is 10 is power 6, right? And then the base unit is not gonna change. So this is how you normally convert from one prefix, right, to a second unit. So now let's do one more problem. What is the volume in milliliter of a cube measuring 2 centimeter in a side? So let's say if you have a cube, and each side of the cube is 2 centimeter, 2 centimeter, 2 centimeter, 2 centimeter. So what's the volume? So we already know the volume of the cube is length time width time height, right? So it's 2 centimeter times 2 centimeter times 2 centimeter, which is 8 cubic centimeter, right? And then how we convert 8 cubic centimeter to 8 ml? Because we know 1 cubic centimeter is equal to 1 ml, if you remember from the previous slide, right? So we can directly convert. If we have 8 cubic centimeter, that means we have 8 ml, right? It's 1 to 1. Now let's talk about the significant figure in the measurement and calculation, right? So whenever we do a measurement, every measurement contain a degree of uncertainty that is due to the inherent limitation of the measuring device that you're using, and sometimes our ability to read it, right? So the degree of uncertainty in a measurement is expressed by the number of digits reported in a numerical value. For example, let's say if we have a scale and then start with 0 centimeter, 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, right? Let's say this is a scale, and if we want to measure a pen or any stick, let's say this is the stick that we're gonna measure. What should be the length of this stick if we use the ruler that we just drew it on the top? So it can be 2 point, you can say 4, somebody will say 2.5, somebody will say 2.7 centimeter, because the unit is centimeter, right? So different person might have a different number, but what we can say is that we are sure that it is more than 2, right? So depending on the instrument that we are using, we might have a different measurement, right? And then by looking by a different person eye, every person can see it differently, right? So that's why we normally see a different number, right? And this is an uncertainty in the number, right? Somebody will say 2.4, 2.5, 2.7. So this 4, 5 and 7 are uncertain number. We are not sure, right? Because this scale that we drew on the top is not precise, right? But if we make this scale a little bit more precise by drawing or putting some more number between them, 1 2 3 4 5 6 7 8 9 10, now we can put more number to our measurement, right? So this is 2, 1 2 3. So now you guys can say this number can be 2.34 centimeter. Somebody will say 2.35 centimeter, and so on. So if you can see over here, now our numbers are more precise. You have more number in the measurement, right? Now we can for sure say that this stick is 2.3 centimeter at least, but we are not sure about the 4 and 5, right? So depending on which measuring device we are using, we might get a different number of length, different numbers in the measurement, right? So whenever you take a measurement, for example, let's say any random number, 5.34 centimeter. So whenever measurement that you are doing, the last number of that major number is always an uncertain number or an estimated number, you can say. Right? And the rest of the number that you have in that major number we call as a certain number. Why? Because by certainty we can say that 5.3 is the major number, right, for that particular object, but we are not sure about the last unit 4, same as like on all the example that we did on the top over here. So always remember this thing, right? So we can say that uncertainty expressed by the number of digit as significant figure, right? So we can say in a significant figure in a measurement always have some certain number, and the last number is always an uncertain number and estimated number, right? And it depends, all these numbers depends on the type of measuring device used to take a measurement and determines the number of significant number that can be reported. For example, if we get a different number, let's say 7.4573, which one is your uncertain number in there? This 3 is your uncertain number. This is the last number of the major number, right? And all these number are certain number, because for sure we know that the major quantity has at least 7.457457, but for the last number we are not sure, right? Okay, so we already talk about this thing. The significant number in a measurement always have all the certain digit except the last one, uncertain digit, right? So let's take an example. If we want to weigh like something using two different balance, in this case we have some salt. On the left hand side we have one scale that is measuring some salt and is giving you a number 10.4 grams. So you have for to measure this mass, we know we can say for sure this salt mass is at least 10 grams, but this 4 is uncertain number. We are not sure, it can be 10.4, it can be 10.5 depending on the instrument, right? Whereas on the second scale on the right hand side, the same salt is going to, if we measure the same salt, what we're gonna see is that measuring device is giving you this number 4977. So that means all these number are certain number and this last number is your uncertain. But what's the difference between the two measurement over here? So the right side measurement is more precise because you have more decimal places. That means for sure you have more, you can say that the amount of that particular salt is 10.497 with certainty. You can be more precise. But on the left hand side you can say for the same salt the mass is 10.4, which is less precise because you have less number, right? So that's why the device that you're normally using for measurement normally decide how many significant number you have in that particular measurement, right? More the number means more precise is the instrument. Lesser the number in the significant number, that means the instrument that you use is less precise. Right. Now we have to know how we're going to figure it out, how many significant figure you have in any given number in a measurement. So there are some rules that you need to know before you can decide how many significant number or figure you have in that particular measurement. So the first rule says that, let me go over here. The first rule says decimal placed after one or more zero indicate the zeros are significant. For example, if you have the trailing zeros and you have a non-zero number in front of the zeros, right, and then you have a decimal at the end or anywhere in the number, if you have a decimal and if you have a non-zero number in front covering the zero, then all the zeros become significant. So that means how many significant number you have over here? 1, 2, 3, 4, 5. So you have 5 significant number, right? That's the rule says. So let me tell you one more time. For example, if I give you one example, 1, 5, 0, 0, decimal. So first look at the zeros and then see if you have one non-zero number like 1, 2, 3, 4, 5. If you have a non-zero number in front of the zeros and then you have a decimal anywhere, then these zeros will become significant. So the number, how many significant number now you have is, you have 1, 2, 3, 4. So that means you have 4 significant number in here. But another rule says if you have a trailing zeros, you have this 3 0, you have a one non-zero number that in front of the zeros, but if you don't have any decimal in there, if you're missing a decimal, like you don't have any decimal in there, then these zeros are not significant. Only the non-zero parts are significant, like 1 and 2. They are 2 significant number. So both the rule says all non-zero numbers. So the rule says all non-zero number are significant. Right. If you have 1, 2, 3, 4, any non-zero number, but if you have a 0 along with the non-zero number and if you have a decimal in somewhere in between, then the 0 will become significant. But if you don't have a 0, then those zeros, if you don't have a decimal, that means you don't count that zeros as your significant, right? Too. If the other rule says if the number is given in a scientific notation, then you don't need to worry about the exponent, just look the decimal part, right, which is, or the coefficient part, which is 2.30. Again, if you see the last term is 0, but you have a non-zero number in front of it and you have a decimal, so this means that 0 has become also a significant number. So how many significant number you have in this 2.30? 2 and 3 are non-zero, that means they are significant, but because of the decimal this 0 also becomes significant. So you have 3 significant number in here. So the next rule, it says if you have a leading 0 and you don't have any non-zero number covering those zeros, if you see you don't have any non-zero number, you still have 0 that is covering all the zeros in front of it, right? So those zeros are not significant. So how many significant number you have in there? Just 2, 1 and 2, because 2 and 5 are non-zero number, so 2. Let's take about the second example over here, 0.40. So now you have a 0, right, and then you have a decimal, but this 0 doesn't have any non-zero number in front of it, so that means this 0 is not covering by a non-zero number, so this cannot be included in our significant number counting. But this 0 is covered by a non-zero number and you have a decimal, so that means this 0 is significant. So we have 2 significant number, 1 and 2. Right. Then the other rule says if you have a trailing zero and you have a non-zero number covering all the zero but you don't have any decimal in there, that means those three zeros are non-significant. So you have just one significant number in here. You have to have a decimal somewhere in the number if you have to include a zero, and that zero has to be after a non-zero number, right? The same thing happened over here, 340. This zero has a non-zero number 4 in front of it, but the problem is it doesn't have any decimal somewhere in here. If you don't have any decimal, that means this zero is not significant. Now you have just two non-zero number, 3 and 4, two significant number. Right? Let's take an example. If I have 348.000, how many significant number you have in here? So if you can see, these are the zeros, and then these zeros is after a non-zero number after 8, right? And then can we calculate, can we use these 30 as a significant number? Yes, because you have a decimal, and because of the decimal and non-zero number in front of the zero, all these zero become significant. So how many significant number you have in there? 1 2 3 4 5 6 6. But if we wouldn't have that decimal, for example, if we would have, let's do over here, 348,000. Now what's the difference? You still have 30, you have a non-zero number in front of the zero, but the problem is you don't have any decimal anywhere in the number. If you don't have a decimal, that means these 30 cannot be counted as significant. Now you have just only 3 significant number in here, right? Just 3, which is a non-zero number. So this is how you normally calculate a significant number. Now let's talk about the exact number. Right? What are exact number? So exact numbers are measurement obtained by counting. Whenever you count, right, like 1 2 3 4 5, if you can count anything, that are exact number, right? You cannot change that number. For example, 1 dozen is how many? 12 thing, right? If I say a dozen of thing is always a 12 thing, so this is exact number. 1 dozen, 12. If I say 1 day, 24 hours, they are exact, right? It's not changing, right? I can say 1 pen. 1 pen is 1 pen. They're always one, is right? Always a 1 pen, right? So they are exact number. And then the exact number has, this is the important thing, unlimited significant figures. What does it mean? If I say I have 1 pen, how many significant number you have in there? Just 1, because it has one non-zero number, but significant number. But if I say 1.0 pen, how many pen right now I have? It's still 1, but the number of significant number increase by 1, 2. If I say 1.00 pen, right now still I have just 1 pen, right? But the problem is how many significant number we have right now? 3 significant number. Similarly, I can have many 1.0000 pen. How many pen we have? Just 1, still 1 pen, right? But how many significant number in here? 5 significant number. So that means you can add as many 0 after in the exact number. That number will not change, but the number of significant number for that number is gonna change, right? So that means you can have unlimited significant figure for an exact number. Remember this thing, right? Similarly, one more example. If you have a $1, How many significant number? Significant number or figure. 1. If I say I have $1.0, how many significant number? 2, but still I have $1. If I say 1.00, how many significant figure? 3, but still I have $1. So that means the value is not changing, but the number is changing, the significant number, right? So I can have multiple zeros, but still the value will remain the dollar, right? So that means it has unlimited significant figures, right? So let's take some of the example and try to solve this problem and tell which one is exact, which one is measured quantity. If you say 0.007 meter, the time you see a meter, that means you measured something in length. So this is a measured quantity. 50 people, you are counting 1 people, 2 people, 3 people, right? You cannot measure it. It's an exact number of people. So this is exact. 23.00 second. This is a second. This is a metric system. You measure something. Measured quantity. Milligrams, measured quantity. Feet. This is an English system of measuring the length. This is also a measured quantity. If I say, let me give you one more example. If I say 3 oranges, they're exact or measured, because 3 oranges we can count 1, 2, 3 oranges, right? This is just a counting. 3 oranges is always a 3 oranges. Doesn't matter which unit of measurement that you're using. So this is exact, right? So remember how you can figure it out, exact and measured quantity. So this is the same answer that we discussed on the previous slide. Now let's try to figure it out how many significant figures we have in each of the question that we have. We have 0.007 meter. How many significant number? So if you can see over here, we have a non-zero number. We have a decimal. But can we use these 2 zero? No, we cannot use these 2 zero in our significant number. Why? Because we have to have a non-zero number that should covering these zeros, right? But we don't have any non-zero number in here. So that means we have just 7. So one significant number figure, right? SF, significant figure. 50 people. The time I say 50 people, this is an exact number. And for exact number, we have unlimited significant figure, right? This number of second, we have decimal. So we have 3 trailing 0 and we have a decimal, and in front of the 0 we have a non-zero number 3. So all 0 becomes significant, right? So we have 1, 2, 3, 4, 5. 5 significant number. How many on this? D. So we have 0.0004050. So let's see about whether we can use these T zeros in our calculation or in our significant number or not. The time I see 20, we see decimal, right? But we don't have any non-zero number in front of those zeros. So these, all the 3 zeros cannot be counted as a significant number. But can we count this 0 and this 0 as a significant? Because we know non-zero number is significant. So this is 4. This is a non-zero number in front of the 0. And we have a decimal also. That means all 4 are significant. So we have 4 significant number in here. How many significant in here? So now you have 2 trailing 0. We have a non-zero number in front of the zeros. But the problem is we don't have any decimal in here. If we don't have a decimal, that means these 20 cannot be counted as a significant, we just have non-zero number to two sig fig number. Right, so this is how you normally figure out the significant number, by applying the rules. If I give you one more example over here, 10005, how many significant number in here? So the rule says if you have a zeros and then those zeros are in between two non-sig number, non-zero number, you have 1 and 5 covering the zeros, that means all zero also becomes significant. If you have two non-zero number covering the zeros, so that means you have 5 sig fig number in here. Right. Let me give you one more example. If you have 20030, how many significant number in here? The time I see these two zeros are between two non-zero number, but these zeros is a trailing zero, and you don't have any decimal in that number anywhere, so this zero cannot be counted as a significant number. Right, so how many significant number in here? 1 2 3 4. You have 4 sig fig number in here, because these two zeros, why we are counting as a significant? Because this is in between two non-zero number, right? But this zero doesn't have any non-zero number in here, right? Or we don't have any decimal, so that's why we have 4 sig fig number. Okay, so this is the same answer that we just discussed on the previous slide, so it's the same thing. Now let's talk about the calculation of the significant number, right? So sometimes whenever we measure anything, if we have a significant number from any of the measurement, if we multiply those number, we can do many mathematical operation on those number. We can multiply, divide, we can add them, we can subtract them. So there's some rules that you need to follow, so that you know whenever you multiply two different major number or divide two different numbers, how many significant number you should have in your answer, in your final answer, right? So there's some rules that you need to know. And one of the important thing that you need to know is a calculator cannot increase or decrease the certainty of the measurement. Means you cannot increase or decrease the significant number using a calculator. So let's talk about the first rule, which is called as multiplication rule. Multiplication and division rule. So whenever you multiply and divide any two number, your final answer cannot have more significant number than the measure with the fewest number of significant figure. Means whatever the number you are multiplying and divide, if any of those number has the lowest significant number, then your final answer cannot have more than that number of significant number that you have in your original number. For example, how many significant number you are multiplying these three number? 4.570 meter, 3.7 meter, 2.74 meter. So let's say how many significant number you have in the first number? 4. How many on the second? 2, 3, 3. So if you which one is the lowest number, significant number? This is the lowest in your original number, lowest significant number. Significant number, right? So your final answer after multiplying all these three number cannot have more than two significant number in your answer. So let's see it over here. When you multiply these three, your calculator will give you this number, this big number, and the meter cube, right? So make sure whenever you multiply a number, always write your unit along with it. If you don't have a unit, then your number is wrong, right? So that's why we have a meter cube or cubic meter. So your calculator is giving you 46.33066, but how many significant number you have in this number? 1 2 3 4 5 6 7 sig fig number. But how many sig numbers we should have in our answer? Not more than 2, right? So how you're going to convert into 2? So we have to see, this is 1, this is 2, we don't want third, right? So your final answer will be 46 cubic meter, right? So right now let's learn one more thing called round off rule that you may be using in your calculation. So remember this thing, the number that you don't need, if that number is 5 or more than 5, then the previous number will get increased by 1. Previous number will get plus 1, right? If the number that you don't need is 4 less than 5, then the previous number is not gonna change. It's not gonna change, right? So let's see over here why we got 46 over here. So we just needed two significant number. This is 1, this is 2. The third number that we don't need is less than 5. Then the previous number, which is 6, is not gonna change. So you get just 46 cubic meter, right? This is how the round off rule will work, right? Okay. Now let's try to use an addition and subtraction rule. So whenever you add and subtract, your final answer cannot have more places to the right of the decimal than the measured with the fewest places on the right of the decimal. What does it mean? So your final answer cannot have more decimal places than the lowest decimal place you have in your number when you are adding or subtracting it. For example, you are adding 5.4, then you are adding 6.55, then you are adding 7.344. So if you're adding these things, you have to see how many decimal places you have in your numbers. So what is decimal places? Is the places after the decimal. So you have just one decimal place in there, right? After decimal you have just one number. Over here you have 2 decimal place, and in the third number you have 3 decimal place. So whenever you add all these 3 numbers, your final answer cannot have more than 1 decimal place, because you have to look the lowest decimal place in your original number that you are adding with rest of the number, right? So let's say when you add all these 3, you are gonna get 19.294, right? So let's see how many, your calculator will give you 19.294. How many decimal places you have in your number? You have 3 decimal places, but how many we need? Just 1, because this is the lowest one. So how you're gonna do it? You have to apply the round off rule again, right? So you just need 1 decimal place, which is this after the decimal. You don't need the second one, right? And the rest of it. So if we have to write 19 point, we don't want the fourth one, which is more than 5, right? 5 or more than 5. That means the previous number will get increased by 1. So you will get 19.3 centimeter. That's why you are getting over here 19.3 centimeter, right? Through the rules of round off, right? So make sure you know these 2 rules, multiplication and the division. You always look for significant number, not the decimal place. But for addition and subtraction, you always look for decimal place. Always look for lowest number of decimal place, or you can say a decimal place rule, right? So let's try to solve some of the problem using the two rules that we discussed: multiplication and addition, and multiplication and division, and addition and subtraction. So let's try to the first rule. So perform the following calculation, rounding the final answer to the correct number of significant number. So we have three numbers, so let's go do it one by one. So the first number is 56.50 meter times 37.99 meter. So let's try to do the first one. So if you multiply these two numbers, your calculator will give you this 2146.435 meter square, because you are multiplying 2 meter, right? So units are very important. Okay, so you are multiplying it, right? You are multiplying it. So which rule you have to apply? Multiplication and division rule. And which rule? So multiplication and division rule says you always see the lowest significant figure in your answer, right? So the first number has 4, second number also has 4 significant numbers, so there is no choice. Your final answer has to be a 4 significant number, not more than that. But your calculator is giving you a 7 significant number, 1 2 3 4 5 6 7. How you're going to convert into a 4? So let's see over here, we need just 4. So 1 2 3 4. The fifth one we don't want, and this is less than 5, so the previous number won't increase by 1, so it will remain the same. So it's 2.2146 meter square, which has a 4 significant number, 1 2 3 4, right? So we apply the multiplication and division rule in there. Let's do the second problem. The second problem is saying you have to add all these three numbers, right? So when you are adding or subtracting it, which rule you have to apply? You always have to apply that lowest decimal place rule. So let's say how many decimal places you have, right? Remember, not the significant rule, always a decimal place rule for addition and subtraction. So how many decimal places you have in here? 3 decimal places, DP. You have 3 decimal place over here, and you have 2 decimal place after the decimal. So the rule says your answer, final answer, has to have the same decimal place that you have in your answer, in your original number, the lowest decimal place in your original number. So out of the 3 number, which one has the lowest decimal place? This number, which is 2 decimal place. So your final answer cannot have more than 2 decimal places, right? So if you add them all, your answer will be 208, right? And these are grams. But how many decimal places we need? 2. It has 3, right? So we just need to 1 2. We don't want this one. So if we want to do round off, this number is more than 5, so previous number will increase by 1. So your final answer will be 15.21 grams, and this is your answer. Right. Let's do the last one. So in this problem, we are multiplying as well as dividing it, right? We are multiplying 5.70 with 1.0 ml and divide that number by 1.8 gram. So which rule we have to apply? We have to apply multiplication and division rule, because we are using multiplication and division both at the same time. So it doesn't matter. We have to apply significant figure rule. Right? So let's see how many significant number we have. In this 5.70, we have 3 significant number. In 1.0 and 1.8, I have 2 in each of them. When you solve this problem using calculator, you're gonna get this big number, right? Then you will see later on gram will cancel, but you will see later on. But right now our focus in the number of significant number that you're gonna get. So your calculator is gonna give you this big number, which has 10 significant number. But how many we need? Just 2 significant number, because this is the lowest that we have. Lowest, right? So we need 1, 2, we don't want the third one, right? And the third one is more than 5, then previous number will increase by 1. So this is 3.2 ml, right? Which has 2 sig number. So this is our final answer with a 2 sig number, right? So this is how you normally apply both the rules of multiplication, addition, and multiplication and division, and addition and subtraction. Now let's talk about the dimension analysis. So if we talk about, let's take an example. Scientist and medical professional, they usually do a routine calculation, right? They usually every day they normally do a calculation. So the most common type of calculation they do in science is called unit conversion, right? They normally convert a unit of measurement into another unit of measurement, right? If you remember, people around the world is gonna normally use a metric system, that is gallon, feet, miles. But in rest of the world we are normally using metric system, right? Liter, grams, meter. So all these professional has to convert one unit into a second unit, right? So they usually do by unit conversion, right? That is a converting a measurement in one unit into an equivalent into another unit, right? And then we do these unit conversion using a method called dimension analysis method, right? And then we're gonna learn about this method, how we normally do it. So the first type of conversion is a metric unit conversion, right? So both the unit comes from the metric system, but we're gonna see how we can convert one unit of the metric system into another unit of the metric system. So you can read it along how you're gonna solve it, but let's go to the problem directly, and then I'll solve the problem on over here, and then I'll explain you how to solve it. So it says convert 0.500 grams into a milligrams. So basically it is saying if you have 0.500 grams, how many milligrams you have, right? That means grams is the base unit of metric system, right? Grams again base unit. So that means we are converting from metric to a metric, right? But the units are different. One is gram, one is milligrams. So that's why it's a conversion. So how we're gonna convert this unit, right? So the first thing that you need to know, which is very important, how these two units are connected, grams and milligrams. Is there any equivalency between the two units? If I say I have 1 milligram, how many grams I have? The time I say m milli, I know the number, it is 0.001 gram. Or I can say 1 milligram is equal to 10 to the power negative 3 gram. Both is same, right? So so I would use 1 milligram equal to 10 to the power negative 3 gram, because that will be really helpful in my calculation. But you can use also 1 milligram equal to 0.001 gram, right? So now so this is an equivalency I can say, or I can write this equivalency into two ways. I can say I have 1 milligram, that means I have 10 to the power negative 3 grams, right, in a divisible form. Or if I say I have 10 to the power negative 3 grams, that means I have 1 milligrams, right? So remember, for any equivalency or any equivalent number, you can always make two different kind of divisible form, right? And these divisible form we normally call as conversion factor. And this factor is very important to solve any of the problem in dimensional analysis, right? And then we're gonna see how we can use this conversion factor to solve any problem, right? So now let's get back to the problem. I have 0.500 grams multiply. Now we have to see out of the two conversion factor that I have, which conversion factor I have to use to solve this problem. So always remember this thing, whatever the unit that you required, in this case we need milligrams. So you have to choose that conversion factor that has that unit that is required at the top of the divisible form, right? So out of the following, this conversion factor has milligram on the top that we need, right? So that's why I'm using this conversion factor, not this one. So I'm going to write 1 milligram over 10 to the power negative 3 gram. Right. If you see carefully, this gram is on the top, this gram is at the bottom. They can cancel it out each other because they are in divisible form. So they're gonna cancel it out each other, and then what's the only unit left is just milligram. So your answer will be in milligrams. And if you solve this number, you're gonna get 500 decimal milligram. So that means if I say 0.500 grams, that means I'm saying I have 500 decimal milligram, 500 milligram. Right. Okay. So this is how you normally solve it. Let's try to do another problem. A tumor has a diameter of 5.5 nanometer. What's the diameter of the tumor in meter? So the problem is saying if I have 5.5 nanometer of tumor, how many meter of tumor I have, right? You have to convert nanometer into a meter. The time you see this conversion, you should know that is there any relationship between nanometer and meter that we can relate. Then then by the prefix I know 1 nanometer is equal to 10 to the power negative 9 meter. How would I know this thing? Because meter is a base unit. What is nano? Nano is 10 to the power negative 9, right? So the time I know this is the equivalency, I can make two conversion factor again. I can say 1 nanometer is equal to 10 to the power negative 9 meter, or I can say if I have 10 to the power negative 9 meter, I have 1 nanometer. Both are same. So now we're going to decide which conversion factor out of the two which we're going to use to solve this problem. So the time we see over here which unit we required in our final answer, meter. And then I told you whatever the unit we required, it has to be on the top in the conversion factor. So out of the following, we're going to use this conversion factor because the meter is on the top on this conversion factor, right? So let's try to solve this problem. So I have 5.5 nanometer over, then we have to write the conversion factor, multiply meter times 1 nanometer. So nanometer will get cancel it out, same unit up and down in a divisible form, they get cancelled, and the only unit left is meter. So your final answer will be 5.5 times 10 to the power negative 9 meter. Right. And how many significant number we need in our final answer? Because this is two figure, right? 1, 2. And remember this thing, whenever you're making an equivalency, you are not required to see a significant number in a conversion factor. You always see the significant number from the given number, right? From the major number, because 1 nanometer and 10 to the power negative 9 meter, they are exact number, right? So for exact number, we usually don't see how many significant number you have. So remember that thing. You cannot use a significant number from the conversion factor. That's why I'm just using 5.5, right? So you still have two sig fig number. So this answer is right. So this is how you normally solve it. So let's try one more. Suppose you weigh your patient and recording her weight at 125 lb. What is your patient weight in kilogram? So what is given? Weight is given in pound, and pound is in English system. Whenever we weigh or mass, take the mass in pound, that means we are using our English system, right? And it's asking what's your patient weight in kilogram, and the equivalency is already given. 1 kilogram is 2.205 pound. So can I make two conversion factor from this? I can say if I have 1 kg, that means I have 2.205 pound, or I can say if I have 2.205 pound, I have 1 kg. Both are same meaning, but which conversion factor we're gonna use for this to solve this problem? So like I told you, we need our answer in kilogram, so that the conversion factor that has kilogram on the top, we're gonna use that conversion factor to solve our problem, right? So how are you gonna solve it? So you have to write the given number times the conversion factor, kg 2.205 lb. lb is cancelled because they are the same unit up and down, and when you divide these two numbers, you're gonna get 56.689 kg, because this is the only unit left, right? How many significant number we should have in our answer? It has 3 significant number. We cannot use the significant count from this 1 kg equal to 2.205 lb, because they are exact number, right? They are equivalent number. So the only number that we can figure it out has 3 significant number. Your answer has to have 3 significant number. Then this is 1, 2, 3. This fourth one I don't want, but this number is more than 5, so this will increase by 1. So your final answer will be 56.7 kg with a 3 significant number. Okay. Now let's try to do a metric conversion with 2 or more conversion factors. So right now we just use one conversion factor to solve the problem. Now we have a problem that we might have to use 2 or more conversion factor. Right. So let's try to solve a couple of the problem over here. So it says convert 78,000 centimeter to a kilometer. So first we have to see, is there any relationship between centimeter and kilometer? If I say 1 centimeter, can I say 1 centimeter is 10 to the power negative 2 meter? Because cent is 10 to the power negative 2. This is one of the equivalency, right? But centimeter is not connected with kilometer that we needed. So we have to know one more equivalency. Can I say 1 kilometer is 1,000 meter? Yes. So instead of writing 1,000, I'm gonna write 10 to the power 3 meter, 1,000 meter, right? Kilo. Right, so if we can see from the equivalency, centimeter is not connected with a kilometer, but centimeter is connected to a meter, and meter is connected to a kilometer. So meter has to be in between centimeter and kilometer. It's like a bridge that connecting centimeter and kilometer, right? So that means we're gonna use 2 conversion factor. So let's try to solve this thing. We have 78,000 centimeter times. So what's the first conversion factor that we're gonna use? Because this is centimeter, right? We have to cancel it out, the given unit, right? So we have to use the first equivalency, and from the first equivalency we have to write 1 centimeter on the bottom and 10 to the power negative 2 on the top, because we don't want centimeter in our final answer, so we have to cancel it out some way. So that's why I'm writing centimeter on the bottom. Then we have the second conversion factor, which comes from 1 kilometer equal 1000 meter. So now we have a kilometer and our answer has to have kilometer. Then 1 kilometer is on the top and 10 to the power 3 meter on the bottom. If you see carefully, centimeter can cancel it out, meter is gonna cancel it out, so the only unit left is kilometer, and that's what we need in our final answer. So if you solve everything, you're gonna get 78,000 times 10 to the power negative 5 kilometer. You can write your answer something like that, or you can convert into 7.78 kilometer. Both answer is right. Let's say the significant number, how many significant number you have in here. So like I said, we cannot use a significant number from a conversion factor, so the only thing that's left is 78,000 centimeter. So in 78,000, these zeros are not significant because they are trailing zeros and we don't have any decimal, right? So you have only two non-zero numbers to two sig fig number over here, and so that our final answer has to have two sig fig number. So this is as two sig fig number, and also the bottom answer also have two sig fig number, so both answer are right. So this is how you normally solve it, a problem with two or more conversion factor, right? So this is your conversion factor 1 that we use, and this is your conversion factor 2 that we used. Now let's try to do another problem that might use two or more conversion factor to solve the problem. So it says a patient received 25 deciliter of blood. How many milliliter, which is ml, of blood has the patient received? So let's say if I say a deciliter, dl, what is d? D is 10 to the power negative 1, liter is liter, right? So this is our first equivalency. And then, but our answer has to be in milliliter, but there is no relationship between deciliter and milliliter. But I know 1 milliliter is 10 to the power negative 3 liter, and because m is what, milli, 10 to the power negative 3. So that means to go from deciliter to milliliter, we have to cross liter in between. So liter is like a bridge that's connecting deciliter and milliliter, because liter is common in both of them. So let's try to solve this problem over here. So you have 25 deciliter, so you have to convert, you have to cancel it out deciliter, so that means you have to use a first equivalency, put 1 deciliter on the bottom, 10 to the power negative 1 liter on the top. And now our final answer has to be in milliliter, put 1 ml on the bottom top and 10 to the power negative 3 liter on the bottom. So deciliter is going to cancel up and down, liter up and down cancel, the only unit left is milliliter. That's what we required. So if you solve everything, you're gonna get your final answer as 2500 ml. And see if you have the right number of significant figure in your final answer. So how you have to just look for the given number. You have two significant number in here, and you have just two significant number also in your final answer. So that's the correct answer, containing two significant number. Right, SF is your significant figure. So this is how we normally use multiple conversion factor to solve the problem. So this is the table that normally have the relationship between English and metric conversion for length, for mass, and for volume. So if I say a 1 meter, which is a metric system M, is equal to 39.37 inches in English system, or you can say 1.09 yard, both are same. 1 kg, 1 kilogram is 2.205 pound. Right? This is a metric system, this is English system pound. So they are equivalent in different system, right? Measurement system. Similarly, if I say 1 liter in volume in metric system is equal to 1.06 quarts. Quarts is a unit of volume in an English system, right? So this is how you normally get the equivalencies. And if you get the equivalencies, you can make a conversion factor. Right? That's the purpose of giving the equivalency. Again, you have more equivalency over here. 1 quart equal to 2 pints. Right? So now let's try to solve some problem using this equivalency. So the problem says the blood bank has 285 pints. Pint is a unit of volume of type of blood. How many liter of blood you have in this? Right. So where you have seen this pint. So from the table or from the previous slide, I know 2 pint is equal to 1 quart and 1 liter is equal to 1.06 quart. Right. So quart we usually write QT and pint we usually write PT. Right. Okay. So now if we have the starting pint and we need in liters, so there is no relationship directly for pint and liter, but pint is related with quarts and quart is related with liter from the second conversion factor, right? So that means quarts is the middleman, is a bridge that connecting pint and liter. So again, we can solve this problem. 285 pint PT times, then we have to cancel at the pint, so we have to write 1 QT quarts on the top, then 2 PT from the first conversion factor. And now what we need milliliter on the top, because our final answer has to be in liter, so liter and it has to be on the top, and then 1.06 QT on the bottom. And let's say if everything is cancel it out except the liter, PT cancel, QT get cancelled, the only unit left is liter. That's what we required. So if you solve everything, you're gonna get this big number 134.4339 liter. But how many significant number we need in our final answer? We just need 3 significant figure, right? But how many significant figure you have in here? 1 2 3 4 5 6 7 significant number, right? Which is not right. So how to convert this number into a right 3 significant number? We have to see, this is 1, this is 2, this is 3, the fourth one we don't want, and this is less than 5, so this one it does not increase by 1. So your final answer will be 134 liter, which has 3 significant number. Right? So this is how you normally solve it. So make sure you practice all the type of problem that we just discussed. And now let's go to the next topic called density. I think you already heard of this term before, density. I think you already heard this kind of term before, like this material is more dense, and because of dense it's gonna go down into the liquid, right? And if the liquid is less dense. So density is nothing, is like a physical property that relate the mass of the substance to its volume. So that means density, which is usually denoted by D, is equal to the mass divided by the volume. Mass in grams and volume can be in milliliter or cc, cubic centimeter. So each substance or each matter has its own density. For example, if you see this table over here, water has a density of 1 grams per cubic centimeter, iron is 7.87. So if we know the density of any random object or matter, by and by comparing that number with the table given with the standard object, we can figure it out what that object is, right? So that's why density is very important. And what are the unit of density? If you see over here in the formula, density equal to mass over volume. Mass is in gram, volume can be in milliliter, cubic centimeter. These unit cannot be cancelling out. So that why you have gram on the top, ml on the bottom. So unit is grams ml or grams cubic centimeter. So remember this thing, unit is grams ml. We can also use a density as a conversion factor, like we discussed in the dimension analysis, and we're gonna see how we can use the density in the form of a conversion factor, right? Calculate that. Now let's try to do some problem on density. The first problem asks you calculate the density of a sample with the mass. Mass is given for the sample. And the volume of 1.2 ml, right? So what is density? Density is mass over volume. Mass, so what's the mass given? 0.90 grams over 1.2 ml of the volume. If you divide these two numbers, you're gonna get 0.75 grams per ml, right? And then if you're dividing these two numbers, how many significant number you need? Because mass you can measure, 1.2 ml, which is a volume you can measure, so you can use both the number as your significant number. So the top number has two significant number, bottom number has two significant numbers. So your final answer has to be in the two significant number, because this is the lowest significant number that you are using for calculation, right? So this is how you normally solve the problem for the density, right? You just divide it and make sure you write the unit along with it, grams per ml. Okay, now let's try to do one problem on density where you can use density as a conversion factor. So let's try to do this problem. If the density of the acetic acid is 1.05, so that means the density is given 1.05 grams per ml. What is the volume? You have to figure it out. What's the volume of 5 grams of acetic acid? Mass is given, which is 5.0 grams. So how you gonna solve this problem? So we're gonna use density as a conversion factor, right? But before we can use a density as a conversion factor, we have to make an equivalency, because we can make a conversion factor from the equivalent numbers, right? From the equivalency, something equal to something. So the time I see 1.5 grams per ml, what does it mean, right? So it means for every 1 ml of the drop of that acetic acid, you have 1.5 grams of acetic acid in there, right? So this is same like something like this. For example, if you're driving 25 miles per hour What does it mean? For every 1 hour you're driving 25 miles, right? Similarly, for density 1.05 grams per ml, I can say for every 1 ml you have 1.05 grams in it, right? It's the same thing, same analogy. And the time you got this equivalency, I can make a conversion factor. I can say 1 ml of liquid is equal to 1.05 grams of acetic acid, or I can say if I have 1.5 grams of acetic acid, that means I have 1 ml of that liquid, right? So this is how we normally use density as a conversion factor, right? So first we make a density into a equivalency and equivalency into a conversion factor. So now the problem is easy. So what we need was the volume. So what's the unit of volume? Ml. So you're gonna use that conversion factor that has ml on the top, right? So you're gonna use this one. So the given number is 5 grams. Conversion factor is 1 ml over 1.05 grams. Grams unit get cancelled, and the only unit left is ml, that is the required unit of the volume, right? So is ml. So if you divide and multiply these two numbers, you're gonna get 4.7619. What's the unit? Ml, milliliter. But how many significant number you need? You need 2 significant number, right? You need 1 significant number because this is 1, right? So you're gonna use 2 significant number in here, not 1. So this is 1, this is 2. The third one is more than 5, it will increase by 1, so it's 4.8 ml. Right, so this is the amount of volume that you have if you dissolve 5.0 grams of acetic acid, and so that it will have a density of 1.0 grams per ml. Okay, now let's try to do one more. A piece of a metal has a mass of this and a volume of 9.0 cubic centimeter. Use the table to identify the metal. So how you going to identify the metal? Like I told you at the beginning when we are talking about the density, that from the density we can identify the metal, because density is specific for that particular object, right? So if the mass is given, volume is given, divide both of them to figure it out the density. Mass over volume, if you divide these two numbers, you're gonna get 2 significant number answer, 7.9. so the unit is grams per cubic centimeter, right? So if we see the table, water has 1, gold has 19.32, ethanol has 0.9, iron has almost the same density that this unknown metal has. So that means this unknown metal is an iron, made up of iron, because the density is very close to iron. So this is how you normally identify a metal, by comparing the density with the given density. So I mean the density of the unknown metal with the table which have all the density of the all the known metal, right? Okay. Now let's talk about the specific gravity. The another term, specific gravity is a unitless measurement defined as the density of the substance divided by the density of water, and we know the density of water is 1 grams per ml, right? This is constant at 25 degrees Celsius. So specific active gravity is nothing, is the division of density of that particular substance that we are talking about in grams per ml divided by the density of the water, which is grams per ml. If the units are both on the top and the bottom, they're gonna cancel it out. That's why specific gravity is a unitless measurement. They don't have any unit, right? And why we need to figure it out the specific gravity? Because this is an important factor for the diagnosis of several medical condition related to a kidney function. For example, urine specific gravity range from 1.02 to 1.03 in a healthy people. So if you figure it out the specific gravity, and that is for any individual with a kidney function disease, and that if the specific heat for the urine come out to be above or below than that, that means you have some kind of problem with that kidney function. This is how we normally use the specific activity gravity, right? And if you can see over here, this number is a unitless. You don't have a unit associated with this number, right? And I already explained you why this is a unitless measurement. So let's try to solve one problem on this specific gravity. A 5.70 ml of a patient's urine has a mass of this gram. Is this within the normal range of the specific gravity? And then we already know what's the normal range of the specific gravity, right? So let's figure it out. Let's figure out the density of this patient urine sample first. Why? Because what is specific gravity? Specific gravity is the density of the sample over density of water, right? So we have to figure out the density of the sample first. So for density, divide the mass with the volume. 5.98 divided by 5.70, you're gonna get this big number, but we need just three sig fig number, because 5.98 has three sig fig number, 5.70 has three sig fig number. So this is 1.05 grams per ml. Okay, so once we get the density of the sample, now we're going to use the formula for the specific heat, specific gravity, which is the density of the substance, density of water. We just got the density of the substance is 1.05 grams per ml divided by the density of water. We all know the density of water is 1 grams per ml. So you're going to get your specific gravity is 1.05. And this value is higher than the normal range, right? That we already discussed on the previous page or the slide. So that means this patient has some problem with the kidney, right? So this is how you normally calculate the specific gravity. Now let's talk about some doses calculation. So why we need to study about the doses calculation? Because many nurses and healthcare professionals normally use this doses calculation to administer some medication, to know how to calculate the correct amount of medication to give to a patient. That's why we need to know how to calculate this doses calculation, because if you provide a wrong doses to a patient, that might be dangerous for the patient health. So how we normally read the prescribed doses, right? So prescribed doses is a conversion factor, and it's usually written in milligrams of the drug per kg of the body weight. So how many milligrams of that particular drug should be given for a patient for certain kilogram of the body weight, right? For example, a dosage of 8 milligrams per kg means for the patient should receive 8 milligrams of the drug for every 1 gram of the body mass within 24 hours. Right? For every 1 kilogram, you have to give 8 milligrams of the drug. Right? So there are some important abbreviation that we might be seeing in this doses calculation is QD and BID. QID or QD is a dose once per day. Means you have to give the entire amount of the dose in each day. BID means you have to give the entire amount of the dose twice per day. Means divide the total amount by 2 and give every 12 hours, because you have to divide the total doses into 2 equal amount, right? And you have to give twice a day, so each day is 24 hours. You have to give them exactly 12 hours apart, right? So make sure you remember this QED and BID. Okay, so now let's try to solve some problem on doses calculation. Ampicillin, one of the antibiotic, is prescribed for a child weighing 63 pounds at a doses of 20 milligrams per kilogram of the body weight of per day in 4 equally divided doses throughout the day. Right? So what is given in there? It says if the weight of the child is 63 pound, you can give a doses of 20 milligrams per kilogram of a body weight per day, right, in 4 equally divided doses throughout the day. So the question one is express the doses as a conversion factor. Second is how frequently you should give the medication. The third one is how many milligrams should be given to the patient at each administration, right? So you have to solve each of them separately. So let's start with the first one. You have to express the doses as a conversion factor. So from here, if we can see over here, it says the doses has to be 20 milligrams per kilogram of the body weight. So I can say 20 milligrams of ampicillin per kg of the body mass, right? So this is the conversion factor I can use, right? Or I can say for every 1 kg of body mass, we can give 20 milligrams of the drug or ampicillin. So this is how you normally make a conversion factor, right? That we already learned. Let's try the second one. How frequently should the medication be given? So it says the medication should be equally divided into 4 equally doses throughout the day. So we have 24 hours in one day, and you have to divide the doses into 4 equal intervals. So that means every 6 hours, right? So every 6 hours, or you can say 4 times a day is 6 hours each, right? So this is how you normally solve the second one. Then we have the third problem. How many milligrams should be given to the patient at each administration? So the thing is that the doses is given in milligram per kilogram of the body weight, right? So the body weight has to be in kilogram, but the child weight is given in pound. So first you have to convert pound into a kilogram. How many kilogram is 63 pound? So we already know the conversion factor, the equivalency between kilogram and pound. I know 1 kilogram is 2.20 pound, right? So the given number is 63 pound times the first conversion factor is we have to convert pound to kilogram. So kilogram has to be on the top, pound has to be bottom, right? So pound will get cancelled. So the leftover unit is kilogram, right? And once we get the kilogram, then we can use the conversion factor of the doses that we just got on the first problem, right? First part of the problem, which is 200 milligrams of ampicillin per kg of the body weight. So kg will cancel. Then when you solve this number, you're gonna get this number over here, milligrams per day, right? But it says the problem is saying at each administration, how many administration we have to give to the child? 4 per day, right? So I can say in one day we have to give 4 doses, right? And this is the amount per day. So day will get cancelled, and you will get this number 1430 milligram per dose, right? So that means for every time you have to give 1430 milligram of the dose, and you have to give 4 doses of this type in the entire day. And so this is how you normally do the problem. So now let's try to do a second problem like that. So say tetracycline elixir, an antibiotic, is ordered at a doses of 8 milligrams per kilogram of the body weight. So I can make a conversion factor something like this: 8 milligram per 1 kg of the body weight. Right? Or I can say 1 kg body weight should be given 8 milligrams of tetracycline. Right? QD means per day, right? The entire dose per day. For a child weighing 52 lb, how many milligrams of the tetracycline should be given to the child? Right? So the weight of the child is given again in pound. So first we have to convert pound into a kg first. So 52 pound times 1 kg is 2.2045 pound. Right? So pound will get cancelled. Now we got kg, and the time we got the weight in kg, we can use one of these conversion factor that we just made. So we need how many milligrams of tetracycline, so you have to use this conversion factor, which is milligram on the top. So 8.0 milligram. So this is 8.00 milligram. 8.00 milligram over 1 kg. Right? So kg will get cancelled, and when you solve this problem, you're gonna get 189 milligram of the medicine. So you have to give 189 milligram of a medicine per day to a child. Right? So basically, to solve this kind of problem, you always make a conversion factor from the doses, like we did over here. And once we made the conversion factor of the doses, see whether the amount or the weight of the child or the patient is given in the same kg or something else. If something else, you have to convert that unit of the weight into a kg. And then once you convert it, then use the conversion factor of the doses to solve the problem. Right? So this is how you normally calculate the doses problem. Okay, so now let's talk about our next topic, which is temperature scale and conversion. So there are 3 different scales that we normally use to measure the temperature. One is Fahrenheit, second is Celsius, third one is Kelvin. So we're going to talk about each of them separately. So Kelvin is SI unit. So most of the scientists in scientific calculation use Kelvin as a unit for temperature, right? Then we have Fahrenheit scale. This scale can be used as a positive and negative, and used for reporting weather in the United States, basically, right? And not used in the medical field in the United States. So this is not used in the medical field, but they normally use for the reporting weather in the United States, the Fahrenheit, and normally symbol as capital F, Fahrenheit. And it can also use a scale of positive and negative. So the Fahrenheit can be negative or a positive. Then we have a Celsius temperature scale. Again, you can have positive temperature, negative, right? It normally used worldwide other than the United States. So in US we normally use Fahrenheit, but outside the US we normally use as degree Celsius. Right? So in degree Celsius for our body temperature, Our normal body temperature in degrees Celsius is 37 degrees Celsius. If you have less than 35 degrees Celsius, then we can say that we have a hypothermia condition. And if you have more than 40 degrees, then we might have a heat stroke. So this is just the normal number that we normally see which kind of condition the body has. And then now we're gonna learn how to convert one unit of a temperature into another unit of a temperature, like a unit conversion, right? So we have three different units: Fahrenheit, degree Celsius, and Kelvin. So to convert a degree Celsius to Fahrenheit or Fahrenheit to degree Celsius, we're gonna use this equation. Temperature in degree Celsius equal to temperature in Fahrenheit minus 32 divided by 1.8. Right? And if we have to convert a degree Celsius to Kelvin or Kelvin to degree Celsius, then we're going to use this conversion factor, right? So if you have a degree Celsius, if you have a Kelvin, and if you convert in Kelvin into a degree Celsius, you're going to get this equation. Or you can say, if to get the Kelvin, you have to write degree Celsius, add 273.15 to it. So basically you can convert from one unit of temperature into a second unit of temperature by using these two equations separately. Right? The first equation is between degree Fahrenheit and degree Celsius. Second equation is degree Celsius and Kelvin. So let's try to do some problem using this equation, how we can convert a different unit of the temperature. So let's try the first problem. While traveling in Europe, you feel ill and visit a health clinic. Your temperature is 38.2 degrees Celsius. Do you have a fever? What is your body temperature in degree Fahrenheit? So if the temperature is more than 37 degrees Celsius, that means yes, you have a fever. But how you're going to convert that degree Celsius number into a Fahrenheit? You have to use the formula. Right? So we already have the formula. You have to plug in the number. Instead of degree Celsius, put 38.2. 1.8 times 30 plus 32, you're going to get 100.0.7 degree Fahrenheit. So this is how you normally convert a degree Celsius into a Fahrenheit. And the second problem is many birds have a normal body temperature of 106 degree Fahrenheit. So you have to convert this Fahrenheit temperature into a degree Celsius and convert this into a Kelvin. Right? So let's start with the first one. Convert 106 degree Fahrenheit to a degree Celsius. So we have to use this relation, degree Celsius equal to degree Fahrenheit minus 32 by 1.8. Plug in the number 106 minus 32, 1.8, you're gonna get 41 degrees Celsius. Right? And then once you have the degree Celsius available, we know Kelvin is equal to degree Celsius plus 273.15. Right? And this is, we normally use it. Plug in the degree Celsius over here, which is 41, and 273.15 to it, you will get 314 K. So this is a Kelvin. So I can say 106 degree Fahrenheit is equal to 41 degrees Celsius is equal to 314 Kelvin. All are at same temperature but in different unit. Right? So you have to solve the degree Fahrenheit or different unit of the temperature, you have to just plug in the value in the formula and the relation and you will get the number.